All right. Good afternoon, everyone. I'm Kelvin, and here with me is Alan and Frez. And so our project idea is to come up with a novel algorithm to look at frequent item set mining specifically for streaming data. So first of all, why should you care? Well, let's say you're an online retailer. You look through your past recent orders at everybody who's bought an iPod recently. You may also notice that everybody who's bought an iPod also happened to buy headphones. So from this, you might conclude that, well, if a user wants an iPod, they might also want to buy some headphones. So if they add an iPod to their shopping cart, you might also want to recommend headphones to them. Now, using this data, and if you also have some demographic information, you put them all together, and you potentially have a pretty good picture of what your consumer base might be. And so now, using this information, you can probably help do some better targeted advertising, maybe do product recommendation, and maybe help you determine what are good bundle discounts you might offer to your customers, depending on where they are. Now this is all well and good. However, finding these relationships might be quite difficult. Now say you had 10,000 items in your catalog. And if you're just interested in pairwise combinations, then you're already looking at 100 million possible combinations. Now you throw in some demographic information and you've got quite a complicated combinatorics problem. So how do you keep track of all these combinations? I mean, not to mention, these trends can change over time. Say, maybe a month ago people liked to buy iPods with these very lovely speakers, but now a new set of speakers have come out and that's what people are buying now. So you don't want to just run this once and keep using these same trends. So how do you deal with this big problem? This is where our algorithm is hoping to do.
Yeah, so there's three things we have to deal with. One is how do we formalize this intuition of getting trends in consumer data. Another is how do we deal with doing this on large scales where the number of individual items is very large. And the third is how do we adapt this for changing trends. So I'll answer these in approximately that order. So first, I'll introduce frequent item set mining. So this is a popular way in the literature to sort of capture the idea of getting together groups of commonly purchased items. So unlike normal data where you just have at any time you get some item from some finite alphabet, here we have item set data. So each datum is a list of items. So for example, what people purchased for Amazon. Each purchase would be one datum, and it would have everything in their shopping cart and maybe some demographic data about them. So then, given this item set data, we want to find the common n-grams. And an n-gram is just a section of n items that come together, or that come frequently together. So for example, the 1 grams we've seen so far in the iPod and headphone data, the 1 grams were just the common 1 grams were the headphones and the iPods. The common 2 grams are pairs of items that come commonly together, which would be the headphones and the iPod would be a 2 gram. Similarly, a 3 gram would have 3 items, and so on. So how can we go through our data and look for these common n-grams? Well, one very important property that will let us simplify our search is the a priori property. The a priori property states that if an n-gram occurs k times, then every n-1 gram subset in it also must occur k times. For example, if you have a pair of iPods and headphones and that occurs 10 times, then individually the iPods have to occur 10 times and the headphones have to occur 10 times. I mean, this is an intuitive property. So what we can do is we could turn this property on its head and we could say that if we have a list of all the n-grams that occur k times, then we know all the possible n+1 grams must be of the form that all of the n-gram subsets of those n+1 grams are contained in the popular n-grams. So this intuition is what the a priori algorithm uses. So how the a priori algorithm works is it starts with all the common 1 grams, which means it just counts everything. Then it takes all the 1 grams which occur with a certain frequency greater than k, and then it uses this set to make a candidate set for the 2 grams using the a priori property. And then it looks at the candidate set for 2 grams and uses that to make a candidate set for 3 grams. Then it scans through the data, looks for all the 3 grams, and then counts all the 3 grams that were in your candidate set. So it targets what part of the data you're looking at. So we need to do a couple of things. We have to store the candidate set, and using Bloom filters is a very good way to do this. So Bloom filters are space efficient, and they don't give false negatives, just false positives. And in our scenario, having a false positive is okay. We just count an additional data point. False negative is bad because then you can miss something. Also, because we're dealing with a very large alphabet size, we may not be able to count everything exactly, so we use an approximate counting scheme of SpaceSaver. So when we're trying to tally which are the n+1 grams that are the most common, we'll just take all the n+1 grams that are in our candidate set, or rather we'll go through our data and we'll add to space saving the n grams that were in our candidate set. So we narrow what part of the data we're looking at, essentially. Okay, so that's how we can make a more scalable version of a priori. Well, how do we do this for changing distributions? Well, we'll think of our data as arriving in various epochs. So, for example, in the Amazon example, maybe each day is an epoch. We want to see how the distribution of items change from day to day. Well, we can always just naively do a priori from scratch at the beginning of every epoch, but we will be wasting a lot of computational time. So here we use the intuition that things that were popular yesterday will probably be popular today as well. So when we form our candidate sets, we will seed them with information about what was popular in the previous day, so we can look at fewer data items. And yes, that's our basic approach.
Actually, we also look at our errors. We get actually two kinds of errors in our algorithm, and both of them come from the algorithms we use and the data structures we use. So we are using two kinds of data structure. One is for Bloom filter, and one is for space saving algorithm. So we get false positives for Bloom filter, which is a probabilistic error, and the second error comes from space saving algorithm. And this kind of error, it could be adversarial. And so the first one, in the first error, we are, we could include some less frequent items in our data structure and count them as frequent items. This is from Bloom filter. And the second error, you're overcounting items. So, but the main question we want to answer, like the theory is here, is at the end we want to see how these two kind of errors contribute to ranking error. So how many of the k items, the k frequent items we capture. And we're hoping to get an upper bound that can show us a trade-off between the size of our data structure and the accuracy of the overall system.
All right, so just a brief last point on the data set that we're planning to run this on. So we have the AOL queries data set, which has roughly 20 million queries collected from about 650,000 different users. Now, this might not be the most ideal data set that we would have liked to use, but at least we can use this to test the accuracy of our algorithm and whether it's computationally feasible. And lastly, a quick note on how we may be able to parallelize this algorithm if we have several machines or on a multi-core machine. We can perhaps consider our data to be divided into each of the different machines as it comes in, and each of the machines would then do their corresponding counts. We would then compile that from a master machine to put together a Bloom filter and then distribute it to do the next stage of for say like the n+1 grams. And so on and so forth. We're still working a bit on how the exact details, but that's probably the idea. And, so that's it. Thank you for your attention.